welcome to another module. So, in this module we are going to look at LMMSE estimation for an OFDM wireless communication system, alright. So, we would like to look at the linear minimum mean squared error estimation for OFDM, which you already know is orthogonal frequency division multiplexing. In an OFDM system, on the Lth subcarrier, subcarrier we have, well, what do we have? We have YL equals XL into HL plus VL. Well, what is L? L denotes your index of the subcarrier. L is basically the Lth subcarrier that we are talking about. YL is the symbol that is received on the Lth subcarrier, HL is the channel coefficient corresponding to the Lth subcarrier, XL is the symbol transmitted or loaded on the Lth subcarrier, and VL is the noise on the Lth subcarrier. Okay. And we have to estimate the channel coefficient on the HL for the Lth subcarrier. Okay. So, that is what we have to do, and towards doing that, let us first start by talking about the statistics of the noise, that is VL. So, first let us start with the properties of the noise let us start deriving the properties. Let us start by deriving the properties of this noise component, the noise sample capital VL on the subcarrier. Alright. So, let us assume the time domain noise samples. Let the time domain noise samples V0, V1 up to, remember we have up to Vn minus, these are the n time domain noise samples. Let these be IID Gaussian of mean equal to 0 and variance equal to sigma square. What that means, at these noise samples, the small v's, that is we have expected value of Vk equal to 0, expected value of magnitude Vk square, that is a small Vk, magnitude Vk square equals sigma square, and since they are independent, expected value of Vk into V conjugate k tilde equal to 0 if k is not equal to k tilde. So, these we know about the time domain samples small Vk. Now, what can we say about the capital VL, right, which is the noise output on the Lth subcarrier. Remember the capital VLs which are given by the FFT of the noise samples, correct. So, each capital VL you can recall is the Lth FFT point of the noise sample. So, summation k equal to 0 to n minus 1 Vk e to the power of minus j 2 pi KL over N, where N equals your number of, so well N equals the number of subcarriers. Okay. So, now let us find, so this VL is the Lth FFT point of the noise samples. Of your time domain the Lth FFT point of the time domain noise samples. Okay. Now, first observe that VL is a linear combination, that is capital VL is a linear combination of the smalls. So, VL is a the capital VL is a linear combination of Vk, which are the time domain noise samples, and since the small Vk's are Gaussian, right, linear combination of Gaussian noise samples, Gaussian samples or Gaussian random variables yields a Gaussian random variable. Therefore, since the capital VL is a linear combination of the time domain noise sample small Vk, capital VL is in turn a Gaussian noise sample, alright. So, this therefore, this implies a linear combination of Vk, this implies VL is also a Gaussian random variable, alright, that is the first one. Further, if you look at the expected value of VL, that is nothing but the expected value of summation k equal to 0 to n minus 1 Vk e to the power of minus j 2 pi k L over n. Taking the expectation operator inside, this is summation k equal to 0 to n minus 1 expected value of Vk e to the power of minus j 2 pi k L divided by n. Each Vk is 0 mean, expected value of Vk is 0, which means expected value of VL is also 0. Therefore, we can now say that VL is Gaussian. So, we have deduced two properties, one VL is Gaussian, VL is also a 0 mean random variable. There is a noise output VL on the L subcarrier is both Gaussian and it is 0 mean. Now, it remains to deduce the variance of each VL, that is what is expected value of. So, now we want to ask the question, what is the variance of each VL, that is expected value of magnitude of VL square. What is this? Remember, this is also equal to expected value of magnitude of VL V conjugate of L, and I can simplify this as follows: expected value of VL into V conjugate of L this is equal to, well, expected value of, we know the expression for VL, summation k equal to 0 to n minus 1 Vk e to the power of minus j 2 pi KL divided by n into its own conjugate. Now, I am going to write the conjugate with a different index, k is only an index. So, I am going to use here an index k tilde equal to 0 to n minus 1 Vk tilde e to the power of minus j 2 pi k tilde L divided by n, of course, the conjugate. Now, I am going to simplify this together by multiplying out these two, the terms in these two brackets term by term. So, I have k equal to 0 to n minus 1 summation k tilde equal to 0 to n minus 1 V k tilde conjugate e to the power of minus j 2 pi k minus k tilde L by n. Okay. Now, once you take the expectation operator inside, I have something interesting. I have summation k equal to 0 to n minus 1 k tilde equal to 0 to n minus 1 expected value of V k V conjugate k tilde e to the power of minus j 2 pi k minus k tilde L divided by n. And now we know that these two noise samples, that the time domain noise samples, the small vk's are independent, which means expected value, and that is what we have already seen, expected value of vk times vk tilde conjugate equals 0 if k is not equal to k tilde and sigma square if k is equal to k tilde, alright. So, this is equal to 0 if k is not equal to k tilde equal to sigma square if or only if k is equal to k tilde, which means only terms which survive in the summation are when k is equal to k tilde, and therefore, this is for each k only one term corresponding to when k tilde equal to k will survive. So, this will be summation k, and when k equal to k tilde, this is sigma square. So, this is summation k equal to 0 to n minus 1 sigma square e to the power of minus j 2 pi k minus k tilde is 0 divided by n, which is basically 1, e to the power of 0 is 1. So, this is summation k equal to 0 to n minus 1 sigma square, which is equal to sigma square. Therefore, what we have is, if you look at this result, we have expected value of magnitude VL square equals n sigma square. So, VL is Gaussian, that is written by this symbol n, it is normal Gaussian, it is in fact complex Gaussian. So, let us simply write VL is Gaussian, mean equals 0, variance is equal to sigma square, its mean equal to 0 and variance is equal to sigma square, correct, right. So, VL, so we have characterized the noise, the properties of this noise VL, where VL is, remember, this is the noise coefficient across the subgroup. Remember, we need these properties to, in order to find the LMMSE estimate, because the LMMSE estimate depends on knowing, remember, we need to know the variance, alright, the mean and the variance of the noise. Okay. Now, let us go back and let us characterize the prior variance, let us characterize the properties of the channel coefficient HL corresponding to subcarrier L. So, we would like to characterize the properties of the channel coefficient HL. Okay. So, we would like to characterize the properties of the channel coefficient HL. Okay. Now, remember HL, now remember HL, again similar to the noise, HL is the Lth FFT coefficient of the channel taps Hk, that is summation k equal to 0 to L minus 1 Hk e raised to minus j 2 pi KL, that is, this is the Lth FFT coefficient of channel taps H0, H1 up to Hn. L minus 1. Now, what we are going to assume is we are going to assume let these channel taps H0 let these channel taps be 0 mean IID variance is equal to sigma h square. That is, we are assuming the channel taps H0, H1 up to HL minus 1 to be independent, identically distributed with mean 0 and variance sigma h square. As we know, because we are considering the LMMSE estimate, these need not necessarily be Gaussian in nature, right. If we are considering the if they are additionally Gaussian, then this becomes the MMSE estimate, alright. So, for a general LMMSE estimation scenario, these need not be Gaussian. So, we are assuming expected, that is the channel taps, the small h's, remember these are the channel taps, expected hk equal to 0, expected magnitude hk square equal sigma h square, expected magnitude hk into h, let us call this k tilde conjugate equal to 0, because they are independent if k not equal to k tilde. Obviously, if k equal to k tilde, then this becomes sigma h square, alright. Now, again we have HL equals summation k equal to 0 to n minus 1 hk e raised to minus j 2 pi k L by n. If I take the expected value on the left, I also get the expected value on the right, which is equal to, now taking the expected value inside, expectation operator inside, k equal to 0 to n minus 1, expected value of hk e raised to minus j 2 pi k L by n, expected value of each hk equals 0, because we have assumed these to be 0 mean random variables. Therefore, expected value of HL, where HL is the Lth channel coefficient on the Lth subcarrier, expected value of each HL is also 0. So, which means this each HL is also implies HL, the coefficient on the Lth subcarrier, channel coefficient on the Lth subcarrier is also 0 mean. Now, we have to find the variance, that is, what is the expected value of HL H conjugate L, which is the expected value of magnitude HL square, expected value of HL into H conjugate L, which is expected value of magnitude HL square. What is this? This is equal to the expected value of, well, let us again write it, use the same trick or technique that we used earlier. We can write this as expected value of summation k equal to 0 to n minus 1 hk e raised to minus j 2 pi k L divided by n into same thing, but changing the index k tilde equal to 0 to n minus 1 hk tilde e raised to minus j 2 pi k tilde L divided by n conjugate, which is equal to, well, now multiplying term by term, summation k equal to 0 to n minus 1 k tilde equal to 0 to n minus 1 hk conjugate e to the power of minus j 2 pi k minus k tilde L by n, taking the expectation operator inside, all right. taking the expectation operator this gives summation k equal to 0, summation k tilde equal to 0, expected value of course there has to be a conjugate here, expected value of h k h conjugate k tilde e to the power of minus j 2 pi k minus k tilde by n, and now you can see this, sorry, this can only be an L point FFT, sorry, this has to be, because there are only L channel taps, this can only be till L minus 1, this can only be till L minus 1, all the summations are only till L minus 1 because we have only L channel taps. So, this is till L minus 1, L minus 1, L minus 1, and again this is also till L minus 1, this is also till L minus 1, and you realize that this is equal to 0 if k is not equal to k tilde equal to sigma h square if k is equal to k tilde. Hence, the only terms which survive are the ones in which k is equal to k tilde, again similar to the previous derivation. Therefore, this will again be summation k equal to 0 to L minus 1 sigma h square, again e to the power of minus j 0 equals summation k equals 0 to, sorry, L minus 1 sigma h square, which is L times sigma h square. Therefore, what we have now is basically we have expected value of magnitude h L square equals L sigma h square. So, we have the variance of the channel coefficient on the Lth subcarrier assuming IID channel taps small h 0, small h 1 up to small h n minus small h L minus 1, that is assuming L IID channel taps small h 0, small h 1 up to small h L minus 1. So, this is the variance of the channel coefficient HL, where HL is the channel coefficient of the Lth channel coefficient of the Lth subcarrier. Alright, so what we have done today is we have considered the OFDM system model across each subcarriers, assumed IID time domain noise sample 0 mean variance sigma square, derived the properties of the noise VL at the output of the FFT, and we have shown that the noise VL on each subcarrier is Gaussian, 0 mean variance n times sigma square, and we also assumed IID L IID channel taps and demonstrated that the channel coefficient HL is also 0 mean and has a variance L sigma h square. Alright, we are going to use these properties in the subsequent module to compute the LMMSE estimate of the channel coefficient HL on subcarrier L. So, we will stop here. Thank you.